Okay, I think we'll just start first. Okay, so today we're doing oscillations, and I'll try to keep the math lighter and talk more about the physics lah, because I think that the math can get quite heavy for this topic, even though it's not that important. So, first of all, I'm sure you guys are already familiar with the most basic spring mass system, and that will exhibit simple harmonic motion. So it's just when you displace your spring by a distance x, there'll be a restoring force in the other direction, and the force is proportional to the displacement. So F is equals to negative kx. So the negative is because it's the opposite of the displacement. And then you'll get this differential equation, which you can solve through various methods to get the general solution, which I'm sure you all know is a sinusoid. So this is the general solution for x of t. So one thing that I would like to talk about here is the phase thing, like this term. So if you don't know what that is, that's basically just a phase shift. So if you draw the graph, right, let's say this is your sinusoid, you can have another graph. If there's an addition of the phi term, then the graph will be shifted a bit. Okay, my drawing is terrible, but you get the point. The graph will be shifted by a certain amount to the other side. So the amount that is shifted by is basically the phase shift. It's a constant, so you do not have to worry about it too much. It just tells you what the starting position is. It's like an initial condition. And then a few other results that you can derive yourself. These are quite useful. And the way you derive it is you just plug in the max and minimum of cosine and sine. For example, if we know that x is x naught cosine omega t, then equivalently v as a function of time would be negative omega naught x naught sine omega t plus phi. So if you plug in the maximum value of sine, which is equals to 1, then you will just get the maximum velocity is equals to the frequency times the amplitude. Okay, so you can just derive these yourself, and it's quite useful to remember. The more unorthodox ones are like these in example 1.1. So these two functions, which are useful, they were tested in SPhO last year. So the first one is this one. The question in SPhO gave you v as a function of x. So you need to be able to manipulate the equations in order to get what you want. So in this case, right, the way they get this function is just you use the identity, the Pythagorean identity that is sine square plus cosine square is 1. So you can rearrange. So x over x naught. This is just your cosine omega t term plus, so if I square this, plus v over omega naught x naught squared. So this is just your sine squared term. This has to equal to 1. And then you can rearrange the equation. You can get you can get v as a function of x by rearranging this equation. Okay? So that's how the first equation is derived. And then for the second one, it uses a trick that we taught 2 lessons ago. So the one about changing the variables of integration. So you can write, instead of writing a as d squared x dt squared, we can write it as x dot dx dot dx. And then x dot is just v. So we can write it as dv over dx also, v dv dx. So this is just the trick that was taught in the kinematics handout. Yeah. And then you guys should be, if you guys are not already familiar, these are equations of ellipses. So an ellipse is has the form of like x squared over a squared plus y squared over b squared equals 1. Or is it negative? I can't remember. I think it's plus. But this is the general form of an ellipse. So you should be familiar. And then to get the intercept, you can just you can just sub in the values for, which would give like y equals 0 or x equals 0 respectively. Yeah. Okay, so this is just the basic part. I think you guys are quite clear with this already. So the harder part, I mean, the more important part is the physics. So very often, simple harmonic motion appears in real life. There are a few reasons why this is so. Later we'll talk about why they appear so frequently. Uh, in general, to solve such problems, right, we should always try to write the equations of motion using Newton's second law first. And note that it doesn't have to be F equals ma. So you don't have to get it into the form where the acceleration is like uh, proportional to the displacement. You don't necessarily have to get into that form. You can actually get it into like the rotational equivalent also. For example, if it's a angular displacement, theta, you can also get it into theta equals negative k theta. So this will also give you SHM. Or any function doesn't necessarily have to be x, basically I'm trying to say. It can be theta, it can be any other function, as long as it obeys this kind of form, is SHM already. So this idea is illustrated in the example 1.2. Um, a rod of mass m is on two oppositely rotating cylinders. So basically this one is spinning like this one is spinning like this. And then there'll be friction because they tell you that the friction coefficient is mu. So obviously the frictional force from the left will be acting to the right, and the frictional force from the right will be acting to the left. Okay? And the idea is that when you displace the rod by a bit, by a distance x, so if the center now moves here, and then the rod is extended like uh, over here, then the normal forces will increase over here versus over here, which will result in a bigger friction because you know friction is equals to mu n. So it's proportional to the normal force. So when the normal force increases, the friction will also increase. As a result, there'll be a restoring force that is proportional to displacement. The math is shown in more detail below, like the exact steps. So you just balance the forces because there is no movement along the along the vertical direction. There is only movement along the horizontal direction. So you can balance the forces and you get an expression for the force, for the restoring force. And we see that actually it has a linear dependence on the displacement. And then we sub it into our F equals ma, and we see that this is a characteristic differential equation for SHM. So the simple harmonic motion is, the frequency of the simple harmonic motion is this. Okay? Do you guys have any questions about how this works, how this system works? Okay, if don't have, then I'll just move on. Okay, wait, I think I got a question. Can you explain what? Oh, because the left cylinder is rotating like this, and then the right cylinder is rotating like this, right? So then the force that these forces to the right and to the left are what the mass will feel, not what the cylinder will feel. So from the perspective of the mass, right, it will feel a force to the right due to the left, right? Because like the force felt by the cylinder is this direction because friction opposes your motion. And then by Newton's third law, the mass will feel an equal and opposite force to the right now, right? Okay, can. Moving on. Okay, so in the most basic spring mass system, right? Like we always assume that, I mean, it's always true that the equilibrium is when there's no extension of the spring. But sometimes, right, especially in real life, uh, This is not the case because there are external forces acting on an object also, besides just simply the restoring force. So the most common example is when you hang the spring vertically instead. So now there's the mass of the weight pulling down. So we once again still assume that it's a massless spring, but it's just that the mass that it's attached to now has the force of gravity acting on it. And as a result, right, there will be some equilibrium like extension of the spring. So let's say the equilibrium length is zero. So we assume here it's zero natural length. Then there'll be some equilibrium extension, YEQ, which is equals to mg over k. This is just by balancing the force. So the equilibrium has changed position now. It's no longer y equals zero. It's like it is like some non-zero amount. And we want to find out whether the motion is still simple harmonic. So the way we do it is we define a new variable, which is the displacement about the equilibrium. Okay, so this symbol just means delta, just means the change. So delta y is equals to y minus yeq. So this simply means that if my mass is over here, let's say the equilibrium position is yeq is over here, and I displace the amount delta y. So the full length will be delta y plus yeq. Okay? And so we can rearrange. If we call the length from the top to the bottom as y, so then we just get delta y is equals to y minus yeq, which is what we see over here. And then why is this useful? Because this becomes a problem that we know very well. My double dot is equals to mg minus ky. And then when you differentiate both sides, right, it becomes delta y double dot is equals to y double dot. Because like yeq is a constant, so it differentiates to zero. Yeah, so you get like the same equation lah, and then actually the frequency is the same. Okay? So we can apply this idea to like the next example, which is when you submerge a cube underwater. So note here that you need to know the equation for buoyancy force. So there is a restoring force upwards that is equals to rho Vg, where V is the submerged volume and rho is the density of the water. Okay? So once again, right, we try to apply the same framework to solve this example. We first determine what the equilibrium height, the equilibrium depth, what the equilibrium depth will be, which is simply a force balance. So let's say the cube is submerged like this. If we define a distance like this, and we call it h naught, then by simple force balance, we balance the buoyancy force with the gravity. Okay? And then we determine the equilibrium depth. And then step 2 is we define a new variable, which is the displacement of equilibrium. So let's say I go like an extra delta y over here. So that is what this thing is. Then the full depth will be h. Okay? And then we'll get this new equation when it's displaced down by delta y. So note here that we're assuming the liquid level stays fixed lah. It's not like it's not submerged in a cylinder. Then because more of the volume is submerged, the force will increase because the buoyancy force scales with the volume submerged. So we can write the new equation of motion, which is this, which is this stuff. And then most importantly, right, you will see that like the equilibrium terms will cancel, which is this one and this one. Okay, so this will always happen if you did it correctly. If you did the method correctly, right, the equilibrium terms should cancel, and then you'll just get a regular SHM equation. If you didn't, it probably means you messed up somewhere. And then we see that in this case, provided the condition, which is that the cube floats to begin with, we will get SHM. of some angular frequency, where this is the characteristic equation. So a few key pointers to note from this example. One is that you need to be aware that the equilibrium terms should cancel. That means your differential equation shouldn't have extra terms at the back again. The whole point of defining the new variable is to get rid of the extra term behind. So if your equilibrium like terms don't cancel out, right, it probably means you messed up somewhere. But other than that, it's quite standard lah. Like the flow, like these type of questions have the same flow. You always start by trying to write the equation of motion, and then it will reduce to some SHM form, and then from that you can imply the frequency and period and all that stuff. Yeah, so the main point is about the equilibrium terms cancelling. Do you guys have any questions? Does that make sense? Okay, moving on. So the next part is like what I said about why SHM appears so commonly in nature is because very often you'll deal with like small oscillations. So small oscillations are oscillations where the displacement from equilibrium is very small. And in general, right, this becomes SHM because of the Taylor expansion. If you guys don't know, you can expand this. I think we covered in the math set. You can expand a binomial term like this into an infinite series where it goes higher orders of m. So it goes to x cubed plus x to the power of 4 plus so on, all the way to infinity. And if x is smaller than 1, so if x is a fraction, then eventually when x approaches a very big power, let's say 50, then this will approach 0 if x is like much smaller, much smaller than 1. So in general, right, we can just stop this, we can just do an approximation and say, call it a day at the x term, the 1 plus nx term. Or sometimes we need up to x squared term, depending on like what the case is. And the reason this is useful is because we linearize many forces. As you can see, right, this is linearly proportional to x. Even though the relationship might be 1 plus x to the power of 3, it will become linear 1 plus nx by doing a small approximation. So let's do a very simple, not very simple, but let's do a useful example. So this is from the National Team Selection Test in 2022, but it's actually not that hard. So the idea is that you have, okay, so the part A is just determining whether it'll attract or repel, which you can use by your dynamics like knowledge. You just differentiate the potential to determine whether the force is, to determine the direction of the force. And then in this case, it turns out that the direction of the force is repulsive. So I won't talk much more about that. I'll focus more on the second part, which is they want you to determine the angular frequency of small oscillations. So we know that in general, right, this force is gravitational in nature. So we have the form of like GMM over M1, M2 over R squared, generally speaking, like your gravitational force. So that's basically what like the term over here looks like. But the key learning point is that we can expand this denominator. So instead of dealing with the math hard on, right, we can convert our d plus x term into a binomial form, which is by factoring out the d first. And then once you factor out the d, right, this is just your binomial form, which is where, for example, 1 plus x to the power of n, you can approximate it as 1 plus nx plus like the higher order term. So in this case, right, in this specific case, we had to expand to the second order large. The reason is because if we had only expanded to the first order, then it will actually, all the terms will cancel out. Because when you add the first term plus the second term, this term, the nx over d term will just cancel out. And we know that the answer cannot be 0. So we need to expand to one order higher in order to get a physical result. So that's what I mean by, that's what the note then by, you might have to consider second order or higher if your answer doesn't make sense. The other way to do this question would be instead of writing out the potential, you can write out the force, but it's kind of the same thing now because you need to differentiate the potential to get the force. Regardless, um, we see that adding the two expansions will cancel this linear term, so we get a form that looks like this for the potential. And we notice some similarities, which is that for a harmonic oscillator, the spring force is half kx squared. I mean, the spring potential. So it scales with x squared, and then this one also scales with x squared. So we can therefore conclude, because force is related to potential, it means that these two forms must be equivalent. And we can just plug out the constant in front, this thing, the k effective, which is the front part of this term. Okay, to determine the angular frequency. So note here that they never explicitly tell you it's gravitational, which means that actually, right, the force doesn't have to be r squared. It can actually be anything else. It will also, uh, you can also do the same method. So yeah, do you guys have any questions about this example? You'll see this a lot in problems below and just in general, where you have to expand a term to make it small. And the way you tell from a question whether or not you should do this is you simply do your reading comprehension. Usually when they say something like X much smaller than D or small oscillations, these are keywords that are hinting you to consider a small order expansion. It can be binomial, most often is binomial, but it could also be small angle approximations. For example, sine theta can approximate as theta, or cosine theta can approximate as 1 minus theta squared over 2. Generally speaking, these are the hints for you. They are trying to tell you to do some Taylor expansion or something, and then take the lower order terms. Can? Okay, moving on. So the next thing is energy. So actually, we kind of talked about energy before we went into energy, but it's fine. Uh, in general, any conservative, so if you guys remember what conservative means, it just means that there's a potential function associated with it. Uh, it is described as some potential that's a function of the coordinates of the position usually. So this can be, by generalized coordinate, it doesn't have to, it just means that it can be like x, y, z. It can really be anything that describes the point in space that it's at. So the potential energy is maximized at equilibrium, is minimized at equilibrium points. Therefore, the um, derivative has to be set to zero because it's a stationary point. Okay, so if we know the potential function of some system, we can therefore determine where the equilibrium positions are by asserting this condition. Uh, the next thing to talk about is stable versus unstable equilibrium. So I think as the name implies, stable is like it will tend back to its equilibrium position. Whereas unstable is, if you push it, it will just fall over and exit the equilibrium state. So it will not return back to the equilibrium already, is basically what it's saying. So, for example, right, if you hang a pendulum like this and you let it go, it will go back to the equilibrium over here. So this is stable equilibrium. But if you hang the pendulum upside down, then it's just going to fall. It's not going to return back. So this is like unstable. Like if you have a rod, I mean, not a string. If this is a rod, technically this is equilibrium because of stay put. But if you push it, it will come back. It won't come back up. It'll just like fall down. So that's unstable. Um, Mathematically speaking, we have this thing. This, don't be alarmed. This is just a Taylor expansion where instead of expanding a general function f of x, we're expanding the potential function u of q. Okay, and uh, if we assume that oscillations are small, once again, we can keep lower order terms. And also we note that the first derivative vanishes at equilibrium. So this term goes to zero. So we are left with this thing. And this is exactly what we saw just now, which is u naught plus half k EFF x squared. So this is the characteristic potential function of a simple harmonic oscillator. Okay, so there's a simple example which is just applying all your math stuff. Uh, I won't go through this. I think that is quite self-explanatory. But I will talk about this one, which is like your conditions for stable and unstable. So in general, right, if the second derivative is smaller than zero, then it tends to be unstable. If the second derivative is bigger than zero, that's how you know it's stable. So these are the conditions that you must assert to determine whether it's stable or unstable. Okay, I have a question. So the question is, I don't get why we drop UQ of naught. Oh, okay. That's because, right, in general, when we talk about dynamics of the system, Newton's second law, we talk about forces. And we know that forces is F is equals to du dx, or du dq in this case, any general coordinate. When you perform the derivative on the constant, it's just going to go to zero. So it won't affect the way the system behaves. The first constant in front is simply telling you what the initial condition is. Does that make sense? Like it won't affect the force acting on the object at all. Because when you perform the derivative, it just goes to zero. Is UQ minus UQ not equals UX? Uh, in general, I don't think so. Because if you think about what you're writing, right, you're saying that the potential at a general like position Q is equals to the potential at equilibrium past potential like in the of the displacement, but there could be other forms of energy like kinetic energy, right? And also, I don't think it's very right to say to define U as a function of X lah. Because U as a function of X is like this term that you plug into the potential function, it's supposed to be like your coordinate in space. But X is not really a coordinate, it's more of like a difference of coordinates. So I think it depends on what the potential function actually is. Because like if the potential function is x squared, right, then I don't think it is. But if it's linear, then yeah, you can just add it like this now. So I think it depends on what the potential function is actually. Okay, I mean you can use the simple like spring harmonic oscillator, right? Like let's say the equilibrium extension is x naught, then is half k x naught plus delta x squared equals to half k delta x squared plus half kx naught squared. Is this true? No, right? Because it's not linear. Uh, like this is not equals right to this. So I don't think it's correct. Okay, yeah. So I think the conclusion is that it depends on the potential function. If it's linear, then yes, I think you can just add like this. But if it's like a quadratic potential function like the spring, you cannot. Because a plus b bracket squared is not equals to a squared plus b squared. Okay. Um, Now we'll talk about damped and driven oscillators. So this is the math heavy part. It's quite rarely tested in SPhO law, so I won't talk too much about it. It's more of applying math. So you basically have like this drag term, which is proportional to the velocity, and when you write out F equals ma, you'll get this differential equation. And then you can solve this differential equation. This is homogeneous, and you can guess a solution, which is of the form a e to the power of s over t, s times t. And then you just plug it in to solve for the initial conditions. So this is the general solution. S1, S2, A1, A2, you need to determine using initial condition. Initial condition just means, for example, x at 0. What is it? What is the displacement at 0? What is the displacement at a certain point in time? That kind of thing. Those are what initial conditions mean, like the velocity at 0 maybe. Okay, so there are three cases of damping. So the first is this, underdamped oscillation. So if you like perform a pendulum experiment in the lab right now, in your school lab, you'll probably get something like this, where the amplitude decays over time, so because of air resistance. So this is when the exponent, so there's this thing called damping coefficient, which is basically like uh, this term goes here, and then you need to analyze the relationship between gamma squared and omega naught squared to determine what case of oscillation it will be. So if y is less than omega naught, you actually get a square root of a negative like number. So it'll be imaginary. This term will be imaginary. And when it's imaginary, that doesn't mean that that doesn't mean that the physical system will explode. It just means that you'll actually still get oscillations. Because if you know complex exponentials, for example, e to the power of I theta equals to cosine theta plus I sine theta, like Euler's identity. So actually, in general, right, when you see a complex exponential, it suggests that there's some sort of oscillation going on. And in this case, it's true because when you write out the final equation of motion, you actually get something of this form where there is both a cosine and a sine term. So this is still an oscillation. But more importantly, that you have a term in front, a decaying exponential term. So this term is the equation of this line, this decaying envelope. As t approach infinity, the amplitude will decay to 0 because air resistance consumes all the energy. And then the second case is if your damping factor is like equals to the critical, is equal to the resonant frequency or the natural frequency, then you will just have this. And the like important thing to remember for this case is just like the system will return to equilibrium in the shortest time possible. That's the difference between this and this. Both of them don't have any oscillations. But for critical damping, it will return to the equilibrium in the shortest time possible. And then case 3 is overdamped, which is when your damping coefficient is very, very big. Your term is very, very big, then you'll just get like no oscillation and it'll just decay to 0 immediately. Okay. We never include any like physical questions for this topic because in general it's not tested and it's just rarely tested because there aren't many insightful applications for it. It's kind of just bashing the math. So if you want to practice this stuff, you can just like practice your math lah. Like try rederiving all these equations by yourself. There's not much physics to it, or like very little. The other one is the driven harmonic oscillator. So this one has more stuff to it, particularly because uh, it's a bit more annoying. So what a driven oscillator is basically like, let's say you have a spring mass system. So apart from the usual spring force that's pulling you back, you could also have like a damping force. So this is like the damping force, this is the spring force. And then on top of that, you add another force that is the driving force. So this force is usually sinusoidal. Okay? Because if it was like a constant force, then it's just a shifted equilibrium law. There's not much to that. The more interesting case is when it's a sinusoidal force of a different frequency. Keyword different frequency. So one is omega naught. So you will get this differential equation where the term on the right represents the driving force. You can work through the math yourself, but more importantly, what I want to help you guys understand is get a physical understanding of what the result means. So when you go through the process of solving everything, right, you should get this kind of general solution. And we notice that the first part is the homogeneous solution, which is when homogeneous just means when all this stuff is set to zero. And when it's set to zero, that just corresponds to your regular damped oscillator lah. So this first part is just the damped oscillator part. The second term is the forced oscillator part. This part is the forced oscillator part. Okay? So the damped oscillators will always decay to zero as time passes on. So most of the time we just kind of like throw it away. And then we just focus on this solution. And we notice that in the steady state just means after a lot of time has passed, it will start oscillating at the same frequency as the driving force, which qualitatively would make sense lah, because you're pushing it, you're applying external energy to it in order to make sure it stays at the same frequency as you. And then to get a physical understanding of what's going on, right? Initially, the frequency might not match. Let's say that it's going faster than the force frequency. If it's going faster than the force frequency, right? That means let's say at one point in time it's going like this, but the force is like this. So it's out of phase with each other. This will cause the force to act as a damping force. So this will slow the object down, if that makes sense. Like if the object moves out of phase with the force, right? The force will be slowing it down, will be like working against it. But then if it's exactly in phase, then the force will always just be pushing it in the correct direction. So regardless of how you start the system, right, eventually it will reach a point where the mass will just follow the external forces frequency, because all the out of phase parts will be like deleted. Okay? And then the last thing to talk about is resonance. So resonance is the state where maximum energy is transferred from the driving force to the oscillating system. So this happens when the driving force has the same frequency as the spring force. The reason is because it will just be acting together lah. Like when you input energy using the driving force, it corresponds to when the spring is oscillating naturally itself also. And then as a result, you kind of have like a infinite energy being input into the system. And then the amplitude will just keep increasing, keep increasing, keep increasing. Because recall what I said just now about how if it's in phase, then the force is doing like positive work on it. If it's out of phase, the force is doing negative work. So if the frequencies match exactly, the natural frequency and the driving force frequency, then you're going to be constantly putting in energy because the force will always be in the same direction of motion as the spring force. And then as a result, the driving force will always be in the same direction of motion as the mass. And then as a result, there'll be positive work done on the mass. And then energy is being put in, it'll just like explode. So the graph looks something like this, where you have like an asymptote to infinity because of the infinite like energy input. But then the moment you add some resistance, right, that scales with the speed, then it won't go to infinity anymore because energy is being lost according to speed lah. Like you'll reach a point where the speed is so high that that'll be equals to the amount of energy being fed in. So when there's slight damping, we see that the not only does the frequency peak changes, but it also like puts a cap on the amplitude, so it won't make it like explode to infinity. And then the more damping you add, obviously the amplitude will decrease. Okay, so the key points to note in this graph are that one, if there's no damping, it can just go all the way to infinity. Second is that as the damping increases, it will change where the peak frequency is at. So peak frequency will no longer be natural frequency. This is very important. When there is damping, the peak frequency is no longer equals to natural frequency. When not damped, the peak frequency is the natural frequency. Okay? So that is the important thing. Okay, and then the last thing, like kind of extra, it's not really, we never put it in the notes because I think it's not very relevant for SPhO, but I'll just talk about it. It's like a different way of solving this differential equation. So instead of like using our regular integration or standard solution guesses, we can actually guess a complex exponential as the answer. So if you guys haven't learned what this is yet, basically it's saying that, so first there's the imaginary number. So imaginary number is square root negative 1. You guys will probably know this. But more importantly, right, if you write an imaginary exponential, e to the power of I omega t, this is actually equals to cosine omega t plus I sine omega t. So this is called Euler's identity. The reason why it's so powerful is because we can reduce like differential equations with cosine and sine inside into exponential problems, and exponentials are infinitely easier to deal with than sinusoids. So in this case, right, if we guess the solution to be e to the I omega t instead, so rather than doing this like guessing a cosine omega t blah blah blah, this is very annoying. We could just guess the solution to be a e to the I omega t. And then you can just plug it in. When you differentiate an exponential, the omega will just come down. So it'll become, if you differentiate once, it'll just become omega a e to the I omega t. Sorry, there's an I in front. So, and then if you differentiate twice, it'll just become negative omega squared a e to the I omega t. The reason the negative appears is because I times I is negative 1. And then you can just sub all these functions into your differential equation to determine what the constant in front should be, what the a should be, and what the omega should be. And then you can check yourself, it should give you the same answer. Okay, but this is just extra lah. You can go read up more about it if you're interested. Not very important. Okay, do you guys have any questions? Okay, if you guys don't have any questions, then I'll give you guys a 5-minute break and then we'll go through the questions. So right now I received requests to go through 2.4, 2.6, 2.10, and 3.2. So do you guys have any other question requests? If you do, during the break, you can message me. If not, then we'll just go through these questions that people requested. Okay, be back by 8:53. Okay, you guys back? Okay, we'll do 2.4 first. So this one actually is not that hard. I think it's like, do you know about moment of inertia? Like the trick is that you need to write it in terms of the angular like rotation. So we have the setup is basically you have a big disk and then you have a small disk, right? So the idea is that you basically need to do a superposition of the moment of inertias. So it's like you just add the moment of inertia first. For a disk, it's half mr squared. So this is for the big disk. And then the small disk, about its own center, I'll use C to denote about the center, is equals to half times small m r squared. So that's if we define this to be r and this to be small r. And then you want to calculate MOI about the center of the big disk. So you just add like the total MOI lah. But do note that you need to add an extra term, which is mr squared. So this term is the parallel axis theorem. Wait, so have you heard of that? I think we will go through it in rotation, but have you heard of that before? Basically, it's like if I know the center of mass of an object about here, about its center, and I want to find it, and I want to find the moment of inertia about a different axis, and this distance r, I can just simply do I is equals to ICM plus mr squared, where m is the mass of the whatever object. It's not just for this. Okay, so you add all the stuff, and then that will give you half. Yeah, and then you can just use. Okay, there's two ways to do it. You can do forces or you can do energy. If you want to do forces, you just use the fact that when it's displaced by a bit, so I'm going to draw this as the center of mass. Okay, so this is the center of mass. Uh, you can take like a small angle approximation because the restoring force will be roughly sine theta, and then you can just approximate that as theta, the restoring torque, I mean. And then you do torque equals I alpha. But I think this position, I think this like method is not that good because you have to find like where the center of mass of the where the center of mass of the big disk plus small disk combined is. So I would recommend you do a energy approach instead, which is that the energy of the system, if it tilts by an angle theta, so let's say it goes an angle theta to the side. The potential energy of the big disk won't change, but the potential energy of the small disk will. Okay, can you see why? Because the center of mass stays fixed up for the big one, but for the small one, it changes out. because it moves up. So then the change in the potential energy of the system will just be the change of potential energy of the small disk, which is equals to m times g times 1 minus cosine theta. So the 1 minus cosine theta term comes from, initially it's at a distance r, now it's at an angle theta, this is still r. So this change in distance is r1 minus cosine theta. Okay, so this is the change in the potential. And then we know that by conservation of energy, change in potential energy must be change in kinetic energy by COE. This must be half times I, so I'll do I effective over here, omega squared. So I'll just write it as theta dot squared, where this is I effective. Okay, so part one is just trying to find the speed. So this one, part one is easy. You can just rearrange for what theta dot is as a function of theta, and then you just do v equals to r times theta dot. Okay? Do you need me to do the math? I think don't need, right? It's just math lah. So this is for part one. Okay. Part two, period of small oscillations. So here is where we use our wait, hang on. Oh yeah, wait, yep. Thanks for pointing that out. Uh, should be two over here. Yep. Okay. Anyways, for part two, they want us to find the period of small oscillations. So the way we can do this is, I think there is no other way. We just have to calculate the torque. Yeah. Okay. Wait. Actually, it's still quite simple. It's just like disk creates some torque because the big disk does not create any torque. So the torque is equals to m times g times theta. So the reason why it's theta over here is because we use a small angle approximation. So technically speaking, the torque is down like this. And then if this is the angle theta, then uh, this is theta. Hey, sorry. This is theta. So this should be 90 minus theta. So then we do cosine, which is equal to sine. So technically speaking, it should be mgr sine theta to get the component of torque or gravity that is acting in this direction. But we do a small angle approximation to get sine theta equals to theta. And then this is equals to, so maybe I should add a negative sign here, to denote that as the angle gets bigger, the torque should act in the opposite direction of an angle getting bigger. This is equals to the moment of inertia times the angular acceleration. So we notice that this is the form of SHM because we can write this as theta double dot is equals to negative mgr over I effective times theta. So this is just SHM with frequency square root mgr over I effective. And then you can just plug in the I effective equation. Okay, can? All good? Okay, nice. Moving on. So next one is a bit more complicated, quite yappy. So first, let's understand what the setup looks like. So basically, the way it looks like is you have like a ceiling, and then you hang a rod down, and then there is a circle, and then you like place one object. Uh, Hang on, let me read. Ah, right. So this is the wire. This thing is the wire, and then it basically exerts a force, a torque, sorry, which is this thing. What this thing is saying, restoring top by angular twist. So it's basically saying that the torque is equals to negative k times theta lah, basically. Uh, okay, so part A is simply just like calculating moments of inertia again. The moment of inertia is 2 times half times m times L over 2 squared because it's a point mass, and then they are at distance L over 2 from the center, and this will yield ml half ml squared, right? Oh, sorry. Okay, and then I theta double dot is just equals to negative k theta. So the period is 2 pi over the omega, which is equals to 2 pi. Okay, yeah, because the angular frequency is k over I. Okay, and then you say you need a step C, right? Okay, so I'll just briefly, I'll just go through the step B quickly. So basically, it's saying that now I put a big mass m over here and a big mass m over here. These are also diametrically opposite, so they're also at a distance, at a length L from each other. And then now what I do is I do uh, a small displacement. Okay, firstly, they want you to calculate this angle. I think you already did that, right? So I won't go through it. This one, you simply use gravitational force. So GMM over like your R squared times L is equals to K times theta. So you should get G is equals to 2 pi square R square L theta, I think. Because they ask you to express it in terms of these variables. Okay? So part C is the one where you have a simple harmonic oscillation. So I will adopt the method, which is that about what we went through just now. let's let theta, okay, firstly, this is r, by the way. So we can write the angle as theta naught plus 2rl. Okay, so let me define stuff here. Theta m is the angular position of the balls measured with respect to this line. So the rotation of this. So this is theta m. It's the full actual rotation. And at any point in time, it can be described as the equilibrium rotated angle plus the extra displaced angle, which is r over l over 2, which is how it becomes 2r over l. And we can do this because it's a small displacement. So if it's a small displacement, right, like the arc length is r theta. So if this is theta and this is r, the arc length is r theta. We can approximate it to be a straight line if it's very small. That's the idea. Okay, so we use the method that we introduced before. Okay, yeah, this theta m thing, maybe I write it like this, easier to explain. Okay, so do you remember just now in the spring case, right? In the like spring hanging off the ceiling, I said that if we define y to be like this, then this is let's say this is y naught and this is delta y, then we have y is equals to y naught plus delta y. It's basically the same thing here, lah. You're defining a new variable. It's just that in this case, our variables are in terms of the angular coordinate. So theta m is just the general like coordinate of big M. Does that make sense? Yeah, and then theta naught is the equilibrium angle is rotated throughout. I'll define this as like this. So the theta naught should be over here, theta naught. Okay, so the balls will oscillate from the equilibrium position. If I call this I'll call this full angle theta m. Then theta m is equal to the equilibrium angle plus any extra displacement. Yeah, correct. Sorry, I should have defined it clearer. Part B, the theta is theta naught. This is the equilibrium angle. So when there is no displacement, this is the balance condition. And then I can displace it by a little bit. I'll call this theta. This is the extra displacement. So theta m is equal to theta naught plus theta. And then I can write the equation of motion. This will give me where I is the torque of is the moment of inertia of the whole system. So there's two contributions to the torque. The first is just it's just from the two rods. From two small masses. Okay, so this is the first equation of motion. How this thing works is gmm over r squared. This is your r squared, the distance between the thing. How do we determine the distance between the thing? We use the fact that r is equals to L over 2 times theta m, which is equals to, wait, sorry. Wait, okay, I'm gonna define the directions a bit differently. I think this should be negative. Yeah, this should be negative because it's like they say that it's perturbed a small angle from the equilibrium position. So if I draw the top view, this is the big M, this is the big M, this is the small m, small m. So if I call this angle theta, then the displacement will be, okay, wait, we can keep the original convention, I think. This is fine. So then I'm calling this distance theta m. And then, okay, does this make, I think this is clearer, right? If I draw it like this. Yeah, okay, my bad, I should have drew this from the start. Okay, then let me explain where this top equation comes from. This is just your GMM over R squared, but your R is L over 2 times your theta m. Okay? So let me erase this. Which is equals to theta naught plus theta squared. Okay, and then don't forget this is torque, so we also need to remember that there is a length term, which is L over 2, right? Oh yeah, right. Sorry. And then uh, we use what we said just now about binomial expansion. So recall that theta plus this thing squared, this is equal, oh sorry, this is negative 2. So we can write this as theta negative 2, factor it out, 1 plus theta over theta naught. So here we're assuming that uh, small angle from equilibrium position. So theta is much, much smaller than theta naught. So we can use the binomial expansion here, and I'll expand it up to first order. 1 minus 2 theta over theta naught. Okay, so this is just the binomial expansion. And so we get, oh, one more thing. Technically, this should be I theta m double dot, but it's the same now. So actually, I'll just leave it. You guys know why this is theta double dot is okay, right? Because if you differentiate both sides, theta m double dot is equals to theta double dot. So it's okay, it's the same. So we get I theta double dot is equals to negative 2 gm ml over L squared over 2. I'll move the 2 up. Okay. Oh, frick. Wait, hang on. There's another term, minus k theta. Don't forget that. K theta m. And then theta m, as we said, is just theta plus theta naught. Uh, okay, so if you see now, we have the first term, which is 4gmm theta naught squared plus uh, 4, wait, sorry, 8gmm over L theta naught cube theta minus k theta plus k theta naught. But remember our equilibrium condition is, so our equilibrium condition is gmm over r squared, where it's basically just L over 2 times theta naught squared is equals to k theta naught. And then this will yield theta naught isn't it negative k theta? Wait, where? Oh, like the end part, yeah, correct. Wait, up to this step, are you guys okay? Oh, wait, okay, wait, hang on. I realized that, yeah, you're right. Okay, someone said the true. Okay, they asked for the answer in terms of, no, okay, so the reason why it looks so weird is because, like, they're asking for the answer in terms of R, not like theta naught. So they want you to work in R itself. R being the equilibrium like distance, like over here. Uh, this one. They want you to express answer in terms of L instead of. Okay, so I'll redo it. I think that this is not the best way. Okay, so in terms of instead of defining it like this, I think the better way to do it is Okay, wait. I think I know what's going on. Okay, so the answer key, like, they for some reason they define theta m to be, they define like this point to be the fixed one, which I think is a bit sus. Like they define the coordinate of theta m to be the big mass with respect to the small mass one. But the big mass doesn't move, so I think that shouldn't be the way to do it. Okay, I'll just do it my way. Uh, so we'll stick to the same convention, but now we need to use the R thing now. So, oh shit, why do they do this stuff where you have both R and theta? Okay, I'll just use the fact that theta naught is equals to. Okay, we'll just do what we did originally. Also, it's not. The 2 in front here should be positive because it's repulsive. Like, wait, no, 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 no. What am I saying? Okay, so I'll do what I did initially, which is this system of equations. But then the only difference being instead of the, like, I don't know why they do this. No, because the thing is, if you look at this term, right, is R, they express it in terms of R and theta naught, which is a bit weird because R is related to theta naught. So I think it'll be more, it make more sense to just express it in terms of R or theta. But it's fine. I'll just express theta naught in terms of R, and then I will substitute it later. So we have GMM. The equilibrium condition for mine will be GMM over L over 2 theta naught squared is equals to k theta naught. Wait, hang on now. There is a length term here. So yeah, it is, it is. Wait, my bad. I just keep copying it wrongly. Hang on now. Let me just. Okay, do you guys understand this part? Like the equilibrium condition? Yeah, okay. So if you look at these, the similarities, right? Actually, I didn't need to expand it out. This term and this first term, they should cancel each other out because 4GMM over L theta naught squared is equals to K theta naught. Agree? Yeah, like these two should add up to zero. Okay, yeah, you're right. Let me write it. Like, because we never explicitly define a direction, so these two should add up to zero. Okay, so then the equilibrium terms will cancel, like this first term and this term will cancel, and then we'll just end up getting the terms that are dependent on theta linearly, which is 2gm, sorry, 8. Oh, actually, it should be k minus this term. Okay, I think it's something like this. Oh. Okay, but this is of the form of SHM, and then I think that you can do another like simplification because they want it in terms of R and not theta naught. So, yeah, you need to convert between them by using the fact that theta naught is 2R over L. Yeah, yeah, yeah. Ah, Yeah, you're supposed to use part B. Okay. Uh, okay, but the point is, you're supposed to write the equation of motion by using this like defining new variable thing. I think that is the main point. The rest is just like math. If it were up to me, I would say that I don't really know why they stick to two conventions because they do both like they ask you to both find r and theta, but they're like the same thing. Like they're just describing what the equilibrium displacement is. I don't know why they do that, lah, but it just makes it a bit annoying. But other than that, the question itself, the physics part is quite basic. It's just the displacement and then the gravitational force increases by r squared, just like the example. Yeah, okay, I can't be bothered to continue. Does this make sense? I will send you their answer lah. But I think like if you solve it in terms of purely theta naught or purely r, I think it's fine lah. Like actually, because the two mean the same thing. They're just coupled by this relationship. Ah, okay, 2.10 is the more interesting one. Uh, okay, so for this one, right? For part one, I mean, okay, firstly, before we even start, you need to know that when you have a mass, like with mass m, like if two identical masses collide, right? Like this one is m, this one is also m. But then one is at a standstill, one has speed v. After the collision, it'll become one moves off with speed v, this one becomes zero. It'll just transfer all the momentum over. This one you know, right? Like you can just easily prove this yourself by doing conservation of momentum, conservation of energy. Yeah, okay. So if you know that already, then you know what happens immediately after the collision. So this one is moving towards the left, right? Towards this one. Then at the instant that this hits this, so if I call this 1, 2, 3, and 4, at the instance that 2 hits 3, the momentum of 2 is instantaneously transferred to 3, which means that 3 will acquire a velocity v instantaneously to the right, and then 2 will instantaneously become 0. So right after the first collision, uh, it'll become like this. Do you agree? It'll look something like this after the first collision. Okay, so if we define the initial position as here, and then we define this distance as, uh, let's just say y, then the equations of motion will be my double dot equals to ky2. So if I call this 1, 2, 3, and 4. So I'm describing the equation of motion for 1 first, is y2 minus y1, ky1. Sorry. minus L. Okay, L being the relaxed length. So the reason why I do y2 minus 1 is because it doesn't have to start. I mean, like, at some point in time, it'll just move off one. Like, maybe it'll be here. It doesn't necessarily have to be, like, you know what I mean, though. Like, okay. And then the equation of motion for, wait, this one. For the second one is something similar also. It's just the opposite because of Newton's third law. So we get a what we call a coupled differential equation where we have two like variables y1 and y2. So how do we solve this differential equation? Okay, firstly, do these differential equations make sense? Like, can you get them? Okay, then I'll teach you how to solve them. So actually, this appears quite frequently. Actually, it appears in RC circuits also. Like the way you would do it is you either do y1, you can try these two first, most commonly, plus or minus. Okay, so in this case, if you add the two together, right, it'll just become zero because they are just opposites of each other. So it'll make more sense to minus. And you'll see why in a sec why minusing makes it useful. If I do y2, wait, y1 minus y2, then you will get 2k over m. Wait, sorry, 2k, not over m. You get this. Okay? And then if you define a variable, let like u be y1 minus y2, then we note that u double dot is equals to y1 double dot minus y2 double dot. And this is just m u double dot is equals to 2k negative u minus L. Wait, sorry, we can just absorb this into our substitution. Wait, I wrote something wrong. Should be, okay? And then can rearrange for u. And this is just the SHF equation. So we know this general solution is u is equals to a cosine omega t plus phi, and I'll just sub in the omega. Omega is square root 2k over m. Okay. And then what do they want us to find? They want us to find the equations of motions of the masses after the first collision and before the second collision. Okay, so this we undo the substitution now, and we use the fact that at time equals 0, hang on, I forgot L term. Remember to add back the L. And then u is y2 minus y1. Okay, so to this step, is it okay? Um, up to here, this one can get. Okay, nice. Then the next step is to write y2 minus y1 is equals to square root 2k over m. I will choose this as a sine function now, so it's easier to differentiate. If you plug in your initial conditions that y2 minus y1 at time 0 must be equals to L at time 0, and then y2 dot minus y1 dot must be equals to negative v at time 0, then you should get a sine phi equals 0, a 2k over m cosine phi equals negative v. Okay, so a sine phi equals 0, we know that the amplitude is obviously non-zero lah, because that doesn't really make sense. So one possible solution is phi is 0. Okay, which will also yield a like this. Okay, so it's just math from here on out, but we also know that momentum has to be conserved, or you can also see it as you must add y1 plus y2 has to be equals to 0, which means that y1 is equal to negative y2 in terms of dots. I mean, like y1 dot and y2 dot. So you can see it as you simply add the two differential equations, or you can also see it as conservation of momentum. Either way, but hang on, wait, I have a question. Oh, okay. Okay, so as I was saying, right, y1 dot plus y2 dot is equals to v, because at any subsequent point they are coupled by a common spring force. So we know that initial condition is that this was at v, this was at 0, so the total momentum is v. So at any subsequent point in time, m, the total momentum must be equals to mv. Okay, so that's how we get y1 dot plus y2 dot equals v, because after the first collision and before the second collision, there is conservation of momentum. And then y1 plus y2 is equals to velocity times time plus c, where c is a constant. Okay, so then with all of this stuff, we can just solve the differential equation now. We can just plug in all the constants. So we get the final equation, which is that y1 is equals to c over 2 plus vt over 2 minus L over 2. So by using these two equations, plus v over 2, oh my god, m over 2k sine m over 2k. Wait, sorry, 2k over m. Can? Which one? Is it the like momentum one, like the y1 plus y2 dot, or is it? I mean, it can only be this, right? This is just like combining all these equations. y1 equals c. Wait, it's just cause like we're just plugging in like these four simultaneous equations now. Like, you know what I mean? As in, we know that y2 minus y1 dot has to be equals to this thing, correct? And we also know that y2 plus y1 dot is equals to v. So this is a simultaneous equation for the dots, right? And then we integrate this expression to get y1 plus y2 equals vt plus c. We can combine this with this, the first one. And then you just add law to solve. For example, uh, you express one in terms of the other, like v1 equals to, yeah, correct. You get it right. Like you just, it's a simultaneous equation now. Yeah, and then you should get like y2 is just the same, but you have negative sign, I think. Like it's plus L over 2 instead. And then minus V over 2, blah, 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 blah. Holy yap. Okay. Oh, shit. Okay, and then after that, it's just like, you just use the result of the first case of the equations of motion. So you have x1 is equals to negative L plus Vt over plus Vt over 2 plus blah, blah, blah. Wait, like the reason why I'm defining it now as x is to represent that, to represent uh now that we're working in the four mass system. So we'll do x1, x2, x3, and x4. Just now it's y1, y2. We only care about the first and second. Now we're doing 1, 2, 3, and 4 to solve part B. Okay, so we define time equals 0. Okay, so before I write the equation of motion, we define time equals 0 as the time immediately after the first collision. Yes, correct. Like the solution is y3, right? Because the like equation of motion is the same. It's just that the starting condition is different. Do you get that part? Yeah. So you basically solve the DE once already. It's just that instead of mass 3 starting at, wait, no, it's the exact same one because mass 3 also starts at V. So yes, exactly, you just find the same DE, but with an extra term in front because the L, there's like a displacement, right? Okay, but anyways, there is like a whole bunch of terms. So I think this is plus VT over 2 plus V over 2 M over 2K sine blah blah blah. Holy. This one has no displacement. It's just this plus a minus that. X3 has VT over 2 plus that. How does my pen keep doing this? Okay, but the point is, we want to find the time before the next collision. And for the next collision to happen, we don't really care about what 1 and 3 is, what 1 and 4 is doing. We only care about what 2 and 3 are doing because we just need 2 and 3 to collide again. So the equation of motion for 2, it should work out to be, this stuff, and then 3 it should be vt over 2 plus v over 2, like all this, the exact same stuff. And then you just equate x2 equals to x3 to find the second collision now. So second collision is when x2 is equals to x3. And the only way for x2 to be equals to x3 is if the terms in the sign thing, so because it's like uh, v2 sine square root 2k over m. Wait, there's another term. Frick. Uh, there's another term v2 equals square root 2k m over 2k. So this has to be equals to like negative v2 blah blah blah. And the only way that is possible is if t is like a multiple, so like pi or 2 pi. Wait, not 2 pi. 2 pi doesn't work. Yeah, so basically the sine thing, 2k over m, it has to evaluate to 0 again, right? Because at t equals 0, it's like 0. You know what I mean? Like at t equals to 0, sine blah 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 is equals to 0. And then when t is equals to delta t, where delta t is what we're trying to find, delta t is the time between the first and second one, your sine thing should evaluate to 0 again, because you need both sides of the equation to be 0. And then in order for it to be 0, it has to be a multiple of pi lah. Either pi, 2 pi, 3 pi. And then obviously pi makes the most sense because it's like immediately the shortest time frame. So the answer should be delta t is equals to pi over m over 2k, like this, because then that will result in sine pi, which will result in 0. So then you'll be at the same like value for both sides, you know. Does this make sense? So at t equals 0, you will start with you'll start with together 2 and 3, and then at t equals this pi over square root m, pi square root m over 2k thing, you will be back to together again. That part can? Why is there only 2 collisions? Oh, because if you notice, right, this is exactly half a period later. Like, pi is exactly half a period later. Which means that it basically went to the situation where you are now stuck with like this. This is at V, this is at 0. This is at 0, this is at V. Oh, shit. So when you transfer the collision again, right, it's just going to become like this. 0, 0, V, and V. Like, you know what I mean? It's exactly half a period later, lah. So the exact opposite of what was initially happening. Yeah, so there will only be two collisions lah, because the left one will become stationary and the right one will just travel away. Yeah, okay. Makes sense? Still don't get where x came from. Which x? Like this equation of motion? It's from solving. No, it's just like doing this. It's the same equation of motion as this. It's just that we define the position. We define the position to be like 0 at x over 2. So then you can get rid of this. Sorry, you define the position to be 0 when x2, where x2 is at time equals 0. Because then you can get rid of this c. Like, you know what I mean? Like that's how come the c in front of the x2 disappeared. Like, as in, you don't have to follow my convention lah. Like, you can do however way you wish. It will still work out to the same answer. Because why is that? Because it's because it'll just have an extra constant term in front of x2 and x3. And then when you equate x2 to x3, is the constant term is just gonna cancel out. So it doesn't really matter. You can define the coordinate system however you want. What's more important is the v terms, like the moving terms lah. The constant terms, they'll just cancel each other out. Those terms that are a function of t are the ones that are more important. Okay, uh, I will quickly go through 3.2. Uh, my bad, I took too long for the Cavendish one. That one was a bit annoying. Okay, I'll quickly go through this. Uh, for this problem, right? Part A, do you need me to go through? Okay. Then I'll just go straight to part 2. So part 2, right? The way we do it is you first use the fact that you need to derive some like simple harmonic thing. So we can simply write, we want the equation of motion to be like this. Okay? So this is because the gravitational force at any point in time would be mg sine theta, where theta is like ds, this is dy, dx. It'll be mg sine theta, this is the force, and then it'll be equals to ma, a being s double dot. So this is always true one. But then we want it to fit the simple harmonic form, right? Which means that we need sine theta to be equals to ks. And then we need our omega to be 2 pi over t naught, because they gave you like the fixed frequency. Okay, so we impose the condition, which is that g sine theta has to be equals to 2 pi over t naught, because we want it to be simple harmonic. Okay, technically it's squared. Wait, sorry. It should be omega square lah. Okay, up to this part, do you understand? Like basically we're just trying to fit the simple harmonic form, because simple harmonic form is s double dot is negative ks. So we're trying to fit it to like some constant now. So the m and the m will cancel. So we need the g sine theta to fit omega squared, right? If that is okay, then the next part is you just solve this differential equation, basically. Not, wait, sorry, you don't solve the differential equation yet. You use the fact that dy over ds is equals to sine theta. And then you can get y as a function of s. So this should give dy ds is equals to this, and then y as a function of s is okay, assuming that y equals 0 at s equals 0, which makes sense lah, the way we defined it here. And then the mechanical energy, that which is what they want, is really like the kinetic energy plus the potential energy law, which is half mgy, which is just half ms dot squared plus half m omega squared s squared. Why is it half mg? Wait, yeah, it's not half mgy. The half is supposed to be on the other side. Sorry. The half is supposed to appear here because you have a factor of 2 under. I wrote it wrongly. Yeah. So this is just the answer for the first part lah, where omega is 2 pi over t naught. You can do the substitution you want. And then part B is the like more annoying one. So parametric equations of x as a function of theta naught and y as a function of theta naught. This one is like kind of math. First, you need to know that tangent theta equals dy dx given, and then we know that s is equals to g over omega squared sine theta. If we differentiate this with respect to theta, you'll see in a second why this is useful. We will get g over omega squared cosine theta. The reason why it's useful is because we can then use the fact that ds squared is equals to dx squared plus dy squared. Okay? Do you see how we set up this differential equation? So what we're trying to do is we're trying to change from, right now we have s as a function of theta, we want x as a function of theta. So we need to find a way to change the variables. And the way we can do so is by writing this relationship, ds equals dx over cosine theta, which is clear from the triangle. Okay? So maybe, actually this isn't that useful. Maybe I should draw it like this. Theta, then cosine theta is dx over ds. Hmm? Why isn't it cosine square? Oh, like over here you mean? Over here is it? Sorry, over here. Is that what you mean? Yeah. Um, I was gonna write it. Okay, but you can just integrate this expression to get x as a function of theta. Uh, cosine squared theta d theta from 0 to theta is equals to. Okay, yeah. So this is the parametric equation for x. Then for y is the same idea, you're just manipulating the differentials again. This time is sine theta over cosine theta, so basically tangent theta lah, times g over omega squared cosine squared theta. Okay, and then you can solve the differential equation again by integrating, and you should get y of theta is equals to g over omega squared half sine squared theta. Okay, so this is the two parametric equations. You can write them in terms of t by expanding omega as a function of the period. Yeah. Do you have any questions? So actually, right, this differential analysis where you do like you draw the triangle and you have ds, dx, and dy is actually very common. Like in statics, some a very famous question is to derive the shape of a hanging chain. That one you also need to use this kind of infinitesimal analysis. It's question is correct. It's correct. It's correct. Yeah. Okay. So that's all. Okay. So yeah, that's all for today. I will rewrite the answer for the Cavendish one. That one I think I didn't do a good job explaining it. So I will try to rewrite something for you guys. Okay, yeah, that's all. Bye bye.